Hi, again, 8th graders. This is another video for your viewing pleasure about a simulation that you will have to download onto your computer. So before I kind of explain it, if you are the type of intrepid individual who would try and just figure this out on your own, you're going to have to go to the website, download it, and then install it onto your computer. Now that you have the Java update, it shouldn't be a big deal, but you can see, well, it's just not coded in HTML, so it's not going to run through the browser. You actually have to host it on your computer. All right, anyway, this simulation is going to be about the relationship between the number of particles in the nucleus of an atom and its atomic weight, or mass, rather. I'm going to use those words interchangeably because so many people do, but they're not the same, just for your future reference. Any atom of an element that has a mass, hold on, restart, rewind all of that. There are atoms of elements that differ in their number of neutrons. They have the same number of protons, like hydrogen has 1 proton, but sometimes instead of having no neutrons, like 99.9885% of the hydrogen atoms have no neutron, there are some that have 1. And then those atoms have a mass number of 2. Okay, that is the general relationship between atomic mass, see, and mass number. Now, okay, so what are some other isotopes that exist, Miss Miller, you ask? Okay, so reset that. How the heck do I add more? Let's do this. Okay, sweet. Cool. It's showing you exactly the most abundant isotope that exists for each element in the first 10, right? If I go to hydrogen, the most abundant isotope is hydrogen 1. No neutron, just the 1 proton. And remember that the proton and the neutron have a very similar mass. So it's not hydrogen 0 because it has 0 neutrons. It's hydrogen 1. All right, cool. Helium 4, 2 protons, 2 neutrons. Lithium 7, 3 protons because it has an atomic number of 3, and 4 neutrons. Some of us have gotten really hung up on whether or not this is a stable or unstable isotope. That's not as important as just understanding that it's the most common. Most of the lithium atoms in the universe are going to be lithium 7. Okay. So let me see what I can teach you about this. Okay, so boron. Boron 11. 5 protons. You figure out for yourself how many neutrons. It only is the most abundant isotope among all the isotopes of boron. It has an 80% abundance. So it's the most abundant, it is. It's just much less abundant than helium, which is 99.99999%. Okay, so boron has 20% isotopes other than boron 11. Those isotopes might be boron 12. Oh, maybe not. It says this isotope has 0%. I don't know, guys. I'm just playing around. I'm starting to look like I have no idea what I'm talking about. But what I want you to take from this is just the fact that isotopes are atoms of an element that differ only in their number of neutrons, and that you can determine how many neutrons are within an atom using the mass number. Okay, sweet. That was fascinating, right, guys? Let's check out what this is. So, you may want to stop watching. I'm totally going to just start playing around now, and I'm not going to edit this video because I'm lazy. But if why don't we just click on that? Wow. Okay. So, this is a way to visualize exactly how many this is hard to say, like just how many of one isotope compared to another there exist in nature. So here's hydrogen 1 compared to hydrogen 2, 99.9885% to this 0.0115%. It's going to basically look like this, a sea of purple with one green, differentiating it because there's an overwhelming number of hydrogen 1s. But if we go to like boron, it's looking a little bit more diverse because you have boron 11 with the green making up most of it, and boron 10 with the purple making up 20% of it, as you saw on the other window. Okay, and I think what they're doing here is that the purples are the lighter isotopes and the greens are the slightly heavier. I'm gonna just venture a guess here that carbon is gonna have. No, it's not a good mix. I don't know. Let's play around with it until we get another one that has a good mix. As you can see, most elements really have one most common isotope, and almost an overwhelming number of carbon atoms are carbon-12. Only just over 1% are carbon-13, and even fewer are that really interesting carbon-14 that you've heard me talk about, which allow us to actually determine how old certain fossils are based on how much radioactive carbon-14 remains in their body. Okay, that I think is all you really need to know about this. Play around with it though. Don't just watch me talk about this. You will learn better if you actually click and compare and try and build the different isotopes. Well, look, neon, that one isn't a 100% like fluorine. So you can actually play around to determine what the other common isotope of neon would be. All right, so that was a little bit long-winded, but hopefully it was helpful, and you're welcome.